Hi, welcome to Fast Physics. This is Unit 2 on electricity and electrostatics. In this particular unit, we're going to begin with electrostatics, or static electricity. That stuff, that force that holds those socks on your sweaters when you pull them out of the dryer. Then we're going to move on and look at electrons and their flow through wires or current. So let's begin by looking at the basic material that you need to understand about electrostatics. There are two different charges, positive charges and negative charges. Negative charges are the kind of charge that are held by electrons. Positive charges are the charges held by protons. Both charges are the same, they're just indicated by a different sign. Opposite charges attract. Like charges repel, whether those charges are both negative or both positive. Electrical charge is a field force. That means that it can act on another particle without directly touching it or making contact. Gravity is also a field force. We feel the effects of gravity from the earth even if we're not touching it. However, gravity is only attractive. It does not repel. Electrical forces are both attractive and repulsive. We indicate the electrical field around particles by using a series of lines. Lines point away from positively charged particles, and lines point towards negatively charged particles. It's important to note that electrical field lines never cross. Notice how the arrows are pointing towards the negative charge. Let's look at an example of two like charges. Lines point away from the positive charge and bend as they get near the other positive charge. The density of the lines in any given area indicate the strength of the field around the particle. So notice that if we imagine an area around the particle that's close to it, there's a greater density of lines per area, and if we go out away, that density decreases. So the charge is greater closer that you get to the particle. Now that you know some key things about electrostatics and how that works, let's take a look at some of the formulas that you're going to need for this section. The first formula you need to be aware of is Coulomb's law. Coulomb's law tells us that the electrical force is equal to Coulomb's constant times the charge of one object times the charge of the second object, all divided by the distance between those squared. Coulomb's constant is equal to 8.99 times 10 to the 9th newtons times meters squared divided by Coulomb squared. All those units are there in order to have things cancel out and work out properly. This proportional relationship is very similar to what we saw with gravitational force. However, in gravitational force, we saw that the force of gravity was equal to the gravitational constant times the mass of one object times the mass of the second object, all divided by the distance squared between those objects. These two formulas represent what are called an inverse square relationship.
Let's take a look at some practice problems now that will allow you to use some of the formulas and concepts that we've talked about.
We know that the charge on the balloon is 5.0 microcoulombs and that it's negative. Micro means 10 to the negative 6. So we have 5.0 times 10 to the negative 6 coulombs of charge. The distance between the two charges is 10 centimeters. We need to convert that into meters by dividing by 100. We have 0.1 meters. Now, if the charge on the balloon is negative 5, then the charge on the cloth must be positive 5 because we just removed the electrons from the cloth to the balloon. We are looking for the electrical force. Our formula for electrical force is Coulomb's constant times the charge of the first one times charge of the second charge divided by the distance squared. Coulomb's constant is 8.99 times 10 to the 9th. So let's insert our values here. Coulomb's constant. And then, while the signs are different, the charges are the same, and so we can simply square those charges and then divide by the square of the distance. Typically, the errors arise in these problems because the parentheses are not entered properly in the computer, into the calculator. So let's break this down. First, we're going to square our charge value and find that answer. Then we're going to take that and multiply it times Coulomb's constant. After we find that answer, then we're going to divide by the square of the distance, giving us an answer of 22.475 newtons. And we can round that to 22.5 newtons. For this problem, we need to find the number of electrons in 2 coulombs of charge. This is a very large amount of charge. 1 electron has a charge of negative 1.6 times 10 to the negative 19 coulombs. To find the number of electrons, we're going to take our charge of 2 coulombs and divide that by the charge of 1 electron to find the total number of electrons. Notice that the coulombs will cancel out, leaving us a number without any units, and that's our number of electrons. And we find that there's 1.25 times 10 to the 19 electrons in this amount of charge. Here are the important key ideas that you need to know from this particular section. First of all, there are 2 kinds of electric charge, positive and negative. Like charges repel and unlike charges attract. Electric charge is conserved, that is, it can't be created, it can't be destroyed, it can just be moved from one place to another. Protons don't move, just electrons. The fundamental unit of charge, E, is the magnitude of the charge of a single electron or proton. This value is 1.60 times 10 to the negative 19 coulombs. Conductors and insulators can be charged by contact. Conductors are also charged by induction. A surface charge can be induced on an insulator by polarization. According to Coulomb's law, the electric force between two charges is proportional to the magnitude of each of the charges and inversely proportional to the square of the distance between them. Electric force is a field force. The resultant electric force on any charge is the vector sum of the individual electric forces on that charge. An electric field exists in the region around a charged object. Electric field strength depends on the magnitude of the charge producing the field and the distance between that charge and a point in the field. The direction of the electric field vector, capital E, is the direction in which an electric force would act on a positive test charge. Field lines are tangent to the electric field vector at any point, and the number of lines is proportional to the magnitude of the field strength.
Now that you've had an opportunity to go over the basics of electrostatics and practice a couple of the questions, you're ready to take the quiz for Unit 2, Lesson 2. Please do this in the Google form through the link found in the teacher notes. Once you have finished that, I will grade it and enter your grade. And while you're waiting for that to occur, please move on to the next lesson, which will prepare you for the second of the 3 quizzes in Unit 2. See you in the next lesson. Bye.